In this last part of section 4.3, we're going to look at some more proof type questions. There's a couple of these kind of questions on your homework, but we'll work out a few here to kind of get an idea of how we're supposed to handle these kind of things. Most of these are going to be where we start with the idea of we have two similar matrices and we want to show either something about those two matrices, or we want to show that some other matrices that we can derive from them are also similar. And note that we're saying here not that A transpose and B transpose are similar to the original matrices, but that they are similar directly to each other. So, where do we want to start with this? Well, we want to start with our assumption. Our assumption here is that A and B are similar. What is our definition of similar? Well, let's just write down that definition. Since A and B are similar, that means there is a non-singular let's just go ahead and abbreviate that, matrix S with the formula B is S inverse AS. And now we're in a position where we can take this information that we have here and apply it to this situation. How can we start with this formula here and look at the transposes? Now, we're just going to bring in some information that we can take from looking back in the book about what happens with transposes. And I'll write out a few relevant formulas. And the book is going to write these in terms of A and B. I'm going to use different matrices so that we can keep them distinct from what we're actually using here. These work for any matrices. So, if we take a product of two matrices and we take the transpose of that product, what do we get? Well, we get the product of the transposes, but in the opposite order. That's always going to be true for any two matrices P and Q that we can multiply together. That their transposes can be multiplied and we get the same, well, at least in the opposite order they can be multiplied, and we get the same result as the transpose of the original product. Another thing that's going to be useful, because we do have an inverse in here, we can note that if we take the inverse of a matrix and we transpose it, then we can actually interchange that transpose and inverse. That the transpose itself is invertible, and its inverse is just the transpose of the inverse of the original P. So these will be two useful formulas. Technically, they're not part of our proof, but they're things that we want to keep in mind. So let's just take the transpose. So B transpose, we'll just apply that to the entire S inverse AS. We'll use the fact that we can go ahead and move the transpose to each factor and then reverse the order. So we have an S transpose, we have an A transpose, and then we have an S inverse transpose. But of course, that's why we brought up this other formula. S inverse transpose is just going to give us, I should go ahead and write out the S transpose A transpose again, but we'll have an S transpose inverse. And we want to see, is this actually the form that we want? Well, the names are not necessarily what we want, but let's rename this. We want to have something like an S here, a non-singular S. Why don't we call this matrix that we got here, this S transpose inverse, a new matrix? We're going to call matrix R this matrix S transpose inverse. In which case, what is R inverse? R inverse is just going to be S transpose. We know it's invertible because it is the inverse of a matrix already. But its inverse is just that whatever matrix we are inverting to get R. Inverses of inverses are the original matrix. And so what do we have here? We have that this S transpose at the front is actually R inverse. So if we rewrite all the S's in this formula in terms of R, we get that this original B transpose is equal to R inverse times A transpose, and then this last part is just an R, where R is a non-singular matrix. And so by definition, A transpose and B transpose are similar. It is just a matter of taking our original B equals S inverse AS and turning that into a new formula for the transposes. Some people like to, when they end a proof, put a little box. This symbolizes that we're done with this proof. This is actually a formal proof. We nothing here was hand waved. This is just what it needs to be. What about part B? Part B is a little trickier because we are dealing with actually a lot of different situations. We're working with all powers of A and B, and we want to show that if we stick with the same power, we're going to, in all cases, get similar matrices. So A squared needs to be similar to B squared, A cubed needs to be similar to B cubed, and so on and so forth. But we are going to start at the same place. We're starting with the same assumption that A and B are similar. And so what does that mean? Then there is a non-singular, again I'm going to abbreviate that, S, with B equal to S inverse AS. Good place to start in all of these problems. Now, how are we going to use this? Well, this one's going to be one where we need to play around with things a little bit. There is a nice way of writing this out in a more formal proof, but it's a little trickier to do right off the bat. We need to play around with things to see what actually happens. And it really is just, let's not jump straight to the kth power like we have in this actual statement, but let's just look at some of the low powers first. Obviously, we don't have to look at k equals 1. That just means we're saying that A and B are similar in the first place, because A to the first power is A and B to the first power is B. So we'll start with the square. We want to show that B squared is similar to A squared, and we want to use this formula. So we'll start with B squared. What is B squared? Well, it's just the square of S inverse AS, because that's what B is. And what is the square? But just multiply it by itself. So we have S inverse AS multiplied to S inverse AS. But then what actually happens here? We have this S times an S inverse. S times S inverse is the identity matrix. I mean, that's what it means to be an inverse matrix. And when we're dealing with products, identity matrices are just play the role of a 1. It's like we're multiplying by 1 in here. And so it just kind of goes away. We get an S inverse A times S, but of course A times A is just A squared. So we actually do have the correct formula here already. B squared is similar to A squared, and we're using exactly the same S. Now, is that always going to be true? Let's look at B cubed. So we have taking the cube of this thing, which just means that we're taking, well, we don't have to write it out as the product of 3 things. Let's look at the square times the S inverse AS. But we already know that the square of this is this over here. So this is really just S inverse A squared S. and then the S inverse AS. Of course, we again have this S times S inverse. So that again goes away. We'll have an A squared next to an A. And so we can immediately write that out as S inverse A cubed S. So we definitely see a pattern here. In each case, we have B squared is similar to A squared, B cubed is similar to A cubed, and the S is the same in each of these cases. And that is going to still be true in general. So if we assume that it's true for k minus 1, so we'll start with b to the k, which just means that we have this to the k minus 1 times S inverse AS. We assumed it worked for k minus 1, so we can actually move that k minus 1 to the A. And now, once again, we have this S times S inverse. We can turn that into a 1, and then we can combine the A to the k minus 1 times A to get an A to the k. So what does this formula mean? That means that since we know it's true for 3, this formula shows it's true for 4. Once we know it's true for 4, this formula shows it's true for 5. And it just keeps going. This is kind of what we call mathematical induction. We're not going to get too much into formal proof theory in this, but it is a pretty common way of proving things that depend on an integer index. In this case, our k is our index. But what this is saying that for any k from 1 to infinity, any positive integer k, a to the k and b to the k are similar. So that one was a little bit more hand-waving than part A, but the idea is still the same. In fact, we got a slightly better result here, in fact, because we actually showed that it didn't matter which k we were working with, we got the same S, which is actually pretty handy. And we will use that in Chapter 6 to solve some problems. We can actually talk more about that when we get to Chapter 6. Problem 13 is very similar to the previous one, where it's only got one part, but we're starting with the fact that A and B are similar. Well, we do need to know that A is non-singular for this to work, but then we want to show that B is non-singular and that the inverses are similar to each other. So, starting off the same way, since A and B are similar, then there is a non-singular matrix S with B equal to S inverse AS. Kind of a running theme here. We're just going to start off the same way every time, because we're starting off with the same idea that A and B are similar, and we want to write down what that means. Now, once we know that A is non-singular, because that's part of our assumptions in this particular problem, what can we say about B in this case? Well, what's a way to actually find out if a matrix is non-singular? We can look at its determinant. So let's look at the determinant of B. That means we're taking the determinant of S inverse AS, and we might want to remind ourselves of a particular formula. Again, let's use different letters here instead of the books A and B that they would have back in whatever chapter. I guess this would be chapter 2. If we have a determinant of a product, then we can just take the product of the determinants. And that's true even if we have 3 things in our product. The determinant of this product is the determinant of S inverse times the determinant of A times the determinant of S. Well, what can we do from here? Well, we actually do have another result. The determinant of an inverse matrix is just 1 over the determinant of the original matrix. Because I don't really have room to put that up there, but I'll go ahead and just write that in here. We have the determinant of S inverse is 1 over the determinant of S. And we have these as they are. And now what happens? Well, these are just real numbers. We couldn't rearrange our matrices. We can't put the S inverse after the A. But we can move the 1 over the determinant of S to after the determinant of A. We're just working with numbers here. So we have 1 over the determinant of S, and we also have a determinant of S. If those are multiplied to each other, we get 1. So what do we end up with? We just have 1 times the determinant of A. So the determinant of B is equal to the determinant of A, and we also assume that A is non-singular. So the determinant of A is not 0. So the determinant of B is also not 0. So since the determinant of B is not 0, B is non-singular. That's the first part. It doesn't actually say anything about the inverses yet. So we still need to show that A inverse and B inverse are similar matrices. Well, here we're going to use another property. So this is very similar to the transposes, where the inverse of a product is equal to the product of inverses, but in the opposite order. That's what we're going to do to work with B inverse. That means we're using the same B is equal to S inverse AS as before, but now we're going to take the inverse of it. So very similar to how we dealt with the transpose. Once we have this formula for the inverse of a product, we can go ahead and apply it here. We have S inverse, we have A inverse, and then we have S inverse inverse. Of course, S inverse inverse is just S. Well, we don't really have to do anything more there. We automatically have it in the right form. So B inverse is similar to A inverse, and we have the same S. So very similar to the previous problem, where our powers use the same S. Here, our inverses use the same S. That's very interesting. In fact, with our notation of what inverse being a negative power, it's almost as if powers are still just following the same rules as our previous problem. So we might make use of that in the future. Now we have one more problem, problem 14. You should know the drill by now. We have A and B are similar matrices, so we're going to start with the same statement. Since A and B are similar, there is a non-singular S. Oops. With B equal to S inverse AS. And do note, I want you to write that every time in your proofs. It's not always assumed that for any A and B, this statement is always going to be true. We want to say that because we know this information from our problem, since that information was given, this is a result, that there is an S that makes this true. So I want to see that, or something similar to this, at the beginning of each of your proofs. Here we're going to be working with a scalar lambda. So this is a Greek letter lambda. There's a reason why we're using lambda here. It's actually pretty standard to use it. Again, this is something that we'll be seeing in Chapter 6. It's called an eigenvalue, or the idea is that we're working with eigenvalues, or trying to work with eigenvalues. But we'll get more into what that means in that chapter. But this is just kind of a preview of some of the stuff that we will be working with. We want to show that the matrix A minus lambda times the identity matrix, so I is the identity matrix, and B minus lambda times the identity matrix are also similar matrices. And then we want to show that their determinants are equal. So let's start with A. This is a little trickier because if we start with B minus lambda I, then it's not too obvious where to go from there. Let's actually start with the A minus lambda I, and let's assume we'll just kind of take a guess here and guess that maybe the same S might work. That's not always going to work in every problem, but maybe it will work here. That'd be very nice. So if we replace the A with A minus lambda times I, are things going to work themselves out? Well, we can expand. This is a matrix product. We have a matrix product of S inverse times a difference of two matrices. So we can go ahead and expand that out. Just distribute the S inverse to both of the terms. So we have an S inverse A, and then we have a minus, well, we could write this as S inverse times lambda times I, but since lambda is a scalar, we can actually put the scalar out in front. So we can write that as lambda times S inverse times I. In fact, we don't even need the I there. We could actually leave that out. Then let's go ahead and do the distribution of the S. We can distribute the S to both of the terms. So the S moves over to here, so we have an S inverse A times S. We saw the minus lambda. We saw the S inverse. And now we're going to multiply on this side by S. But of course, the I is not really too important, so we'll go ahead and leave it out. We have an S inverse S. And what do we have here? We have S inverse AS, and we have an S inverse S. Both of those are things that we already know. S inverse AS, we said that is B. S inverse S is the identity matrix, because we're just dealing with inverses. So what do we've got here? We've got the fact that B minus lambda I is equal to S inverse times A minus lambda I times S. It worked out very nicely. So A minus lambda I and B minus lambda I are similar. Part B actually can follow from one of your exercises and this part A. So once we know that these are similar, you can use one of your problems to actually say something about the determinants right away. So I'm going to leave that to you. I'm going to say left to reader. So if you want, you can try that out. You can ask me questions about that. Feel free to come to my office hours if you get stuck on any of these proofs. And if you want to actually maybe discuss the last part of problem 14. My office hour has been kind of empty lately. If anybody actually wants to show up and keep me company, that'd be great too. So feel free to join me there. And I'll see you guys. Well, actually, I'll see you first in your exam. We're going to have our exams coming up this next week, so get ready for that. Again, you can ask me questions about that in my office hours as well. And then we'll start up on Chapter 5 after the exam. So I'll see you after that.